Yeah. So basically that's pretty much it. So we didn't really invent like concrete coin, we didn't invent asynchronous Byzantine binary consensus, or we didn't invent multiple things. What is maybe our own creation is really putting those building blocks together into a novel algorithm that has some nice properties which were hard to come by before. So yeah, just to remind, it's asynchronous almost, and we hope to improve that. It's scalable because it's based on gossip. It's permissionless because basically it has no problem with dealing in accepting new nodes or rejecting old nodes. It is fully open source and open not just source but open to everyone, and it's relatively simple. Yeah. So the next part we wanted to talk about, and I'll try to be brief about this. We wanted to say a bit about dealing with malice in PARSEC. So the kinds of malice we will cover are forks, are event forging, stalling, and Sybil attacks. There are multiple more possible malicious behaviors, but it's impossible to cover them all. Somebody will always come up with some new one. And apart from that, we also have correctness proofs for PARSEC. So yeah, even if somebody comes up with some new way of trying to be malicious, we should have it covered. And so let's just see how in particular we deal with those types, how PARSEC handles them. So about forks we already talked a bit. We use strongly seeing, we use supermajorities, and this basically lets us deal with forks. But this is not the whole story. So basically we have two lines of defense regarding forks as well. The first line of defense is observers, because observers are required to strongly see interesting events. This has a nice property. So let's assume observers aren't required to strongly see the interesting events. Let's say just seeing is enough or something like that. So now let's say we have this Carol who is notorious for creating forks, and she creates a fork, and then on one fork she has one interesting event, and on another fork she has another interesting event. And she gossips one of those events to a part of the network and another one to another part of the network. And let's say until observers are created, the forks weren't detected. So the observers that see a supermajority of interesting events, actually part of them see one of them and part of them see another one of them. So then we go through the whole consensus. Everybody agrees about which nodes to consider, which interesting events, which nodes to consider and take interesting events created by them. So let's say that Carol passed this test. So basically everybody decides true about Carol, and they will use their interesting event for consensus. But now what happens? Everybody agrees that Carol's event should be used, but a part of the network thinks it's one of the events and the other part of the network thinks it's another one of the events. So now we are in trouble. But since we require strongly seeing, we have a guarantee that if an observer strongly sees one of those events, then no other observer will strongly see the other one. So we are safe. So basically, when we decide that Carol's event should be taken into account, it will only be one of those, never the other one. So that's okay. And the other line of defense during making a decision is actually requiring a supermajority of agreeing values. Because, let's assume that even though we have this requirement, somehow we managed to decide two different values. So some honest nodes have seen a supermajority of auxiliary values false, and some honest nodes have seen a supermajority of auxiliary values of true. And basically this tricked part of them to decide true and a part of them to decide false. But what happens? Basically any two supermajorities have an honest node in common, which basically would mean that there was an honest node that had an auxiliary value of both false and true, which cannot happen because it was an honest node. So we are safe once again, and everything is good in the world. So forks aren't a problem. How about forging events? So basically, we have two possibilities here. We can forge an event and try to come up with some artificial event that nobody really created and send it in gossip to somebody else and try to trick them into incorporating it into their own graph. But basically what this does, it ends up with creating a fork, because there are no events that would have this event, that would refer to this event, because there are no events. Well, this is a totally new event. No other event could refer by hash to this one. And basically it's pretty impossible that that somebody will invent an event that fits an existing hash. This is basically a pre-image attack, and cryptographic hashes are thought quite resilient to that. So this one is taken care of. The second possibility is somebody sends us an event and claims that this event was created by somebody else. But this is where cryptographic signatures come into play. And basically, unless somebody breaks elliptic curve signatures, then we are safe from that as well. So another part, stalling. So let's say malicious nodes collectively decide to try to stall us and do nothing, and not respond to anything, and hope that we will wait for them indefinitely, and basically they will break our network. But as long as there is less than a third of them, there is still a supermajority of honest nodes, and the messages from honest nodes will eventually propagate. And we never wait for more than a supermajority. So a supermajority is always enough to make a progress. So as long as we have an honest supermajority in the network, we are fine. We will make progress, and those guys can just strike us as much as they want. They will do nothing to us. So stalling is also fine. And final thing, Sybil attacks. So basically, what are Sybil attacks? You might be a bit familiar, because blockchain is a famous way, proof of work even on a blockchain, is a famous way to deal with that. So Sybil attack is mostly inventing a lot of fake identities and then pretending to be a lot of independent parties and trying to take control of a network this way. So with proof of work, it doesn't really matter. Number of identities doesn't do you anything good, because you need to do work. Yeah? So you are bounded by your computational power and not by the number of identities you can invent. Here, we actually don't have really anything in PARSEC itself that would prevent Sybil attacks. There are parts of routing like node aging and random relocations and things like that that we won't go deeper into that work towards preventing this. And an important thing is that a lot of malicious behaviors are detectable. Forks are detectable. Trying to forge a signature is detectable. Trying to forge an event is detectable. So basically, if somebody doesn't answer for some time, well, basically we will drop them out of the network, because why keep an unresponsive node, right? So basically we will punish malicious behaviors and get rid of the nodes that are potentially malicious or just non-functional, which basically means that unless somebody does a really well-coordinated attack and spawns a lot of nodes that would take over a third of the network, we should be safe. So this is basically our way of preventing this kind of attacks. And yeah, so now I will let Pierre summarize where we are at this point.
Yeah. Just one small point as well on Sybil attacks is that on the safe network specifically, there would be a cost to it, since we are going to have a cryptocurrency and there will be a cost to performing some operations on the network. Right. So yeah, there is also economic incentives to, well, disincentives to Sybil attacks. So yeah, just kind of wrap-up slides. Are we there yet? So the white paper is there yet. You can review it. You can fix our synchrony problem. In terms of implementation, the code is on GitHub. So currently it handles static membership. We're working on dynamic membership right now, and also we're working on making it production ready. So currently we would advise to look at the code, test, use the examples, play with it, get a feel for it. But we are going to go full-on testing, full-on comprehensive documentation, make sure we iron out any performance bottleneck, and so we'll let the world know when it's production ready, and then and that's also going to include supporting dynamic membership, and then any open source project will be very welcome to use it for their own purpose.
Or even improve it if they have an idea for that.
And of course, improvements welcome. And finally, in terms of the safe network, are we there yet? We're currently in Alpha 2, so for all the details, go to our website, safenetwork.tech, and go to safenetwork.tech/timeline. You're going to have much more details. But basically what we've got is Alpha 2, which is something that you can play with. You've got a browser, you have an API, you can create apps, but the backend is all hosted on the cloud. And so Alpha 3 is going to be switched that to our routing that we described here and PARSEC for consensus, and so get rid of the cloud-hosted network and actually make a peer-to-peer network out of it. So we've already got Crust, which is the layer below, which connects networks in a peer-to-peer. So we're really just consensus, and routing is the next step. After this, Alpha 4, and which may or may not be the last alpha, will be implementing SafeCon, the cryptocurrency, and hosting big data. So in the first time with Alpha 3, we're just going to be looking at, for instance, the kind of data that's needed to maintain the topology of the network. And then we'll consider how to deal with big data in Alpha 4. So thanks, everyone. Thanks to the sponsors, UT, who's hosting us, Volt, who I think is a sponsor of this, and Work On Blockchain, of course, who did the hard job of organizing this. Thank you.
Thanks.